Hello, welcome. I know by now you've watched previous episode because this is episode number 30 of the static mechanics, which I think the last five episodes we were dealing with three coplanar forces that are in equilibrium, making use of the Lami's theorem. We can also use the vector approach or the triangular forces. So in this question or in this episode, we have a body of mass which is 50 kilogram is being held in equilibrium by two ropes whose weight may be ignored. The weight of the ropes are ignored, so they are not going to affect the calculation. So one of the rope is attached to a point above and the other to the left of the mass, making an angle of 15 with the vertical, whilst the other makes an angle of 30 with the downward vertical. We have to calculate the tension in the rope. Now we are having two ropes, we are having two angles. Let's take this part of the sentence again. One of the rope is attached to the point above, right? The point above. Then let's ignore the other one here, okay? So from here, one of the rope is attached to the point above, making an angle of 15 with the vertical. The above is making an angle of what? 15 with the vertical. And the other to the left of the mass, which makes an angle of 30 with the downward vertical. So now we see that the 15 is for the first rope and the 30 is for the second rope. So what do? We indicate this by diagram. Let's see if we have the object, is it object, a body, which is in there. The body will be having a weight downward, since we have our W, which is equals to mg, and mg is what? Mass times or gravity. The mass is 50, gravity is 10. So I am going straight forward and have my 500 what? Newton. You can show that because of space, I am going to truncate some of them. Then, if the rope is above here, it means the rope is attached to some surface. The rope cannot be in space. So let's indicate some space, what do you call it? A surface on which that rope can be attached. So if this is the surface, we can attach the rope here. So we have the tension in here to be the tension number 1. Now, when the rope is attached, we were told that it makes an angle of what? 15 degrees with the vertical. What will be the vertical? Do we have any vertical line there? We have to introduce a vertical line in there. So if I introduce a vertical line, I should have that place having 15 degree angle. If that is 15, the opposite will be taken from what? 90. Then the other rope is attached to the left of the mass. This is the mass. This place is the left of the mass. When we attach it to the left of the mass, it makes an angle of 30 with the vertical. What is the vertical here? If I put any rope here, the only vertical I'll see will be the force moving down. So let's make the other rope attached. Let's see somewhere here, not far. Okay, this is also going to be tension number 2, making an angle of what? 30 degrees. Okay, that is it. I think these are the two informations provided in the question, but we can extend this further to be able to resolve it either using the vector approach or using Lami's. What can I do? Let's see if I introduce a horizontal here, which is going to be parallel to the surface on which the first rope is attached. You see, if that is done, this area is going to be 90 degrees because it's perpendicular. Here will also be 90 degrees because it's perpendicular. If that is true, it means this is parallel to this horizontal. So the angle here will be equal to this angle. And what angle will be here? This minus 90, because that is perpendicular lines, will give you 75, right? 75. So here will also be 75. By what property? Alternate angles. Alternate angles are equal because this is parallel to the surface index. Then what happened? If here is going to be 30, here is 60. Remember, not drawn to scale. So don't judge my diagram. Since we are seeing the mistake, when you are drawing, you draw the 30 closer, or I should correct myself and see if I bring the 30 closer, it will be reasonable to call the other side 60, right? So I can call here as what? 30. Then the tension will now be here as what? T2. The other angle we are calling will be 60 degrees. All right, we are on course. 60 plus 30 plus 90 give you 180. We also need the tops to also be 180. So this is going to be 180 minus what do you call it? 75. That will be giving you 105. So I should be having 105 here. Would that be possible? 105. Okay, this is not a straight line, so this is the only straight line. 180, 180. So perfect. We have our diagram, have all the angles completed. So if you want to use triangular approach, you draw a triangle. If you want to use vector approach, you just resolve the values here into vector column form. Since we are using Lami's, we need to draw a diagram to introduce that. I think this is T1. Then let's see, we have our vertical, not drawn to scale, as I said earlier on. So if I have my W, I have my T2, then I have my T1. The angle here is the angle between T1 and T2, which is the whole angle. That will give you 165, right? Let me close here. 165 degree. The angle between W and T1 still remain 30 degree. This is 90 plus, what do you call it, 75, will still give you 165 degree. So these are the information that we can use with our Lami's theorem. So let's go. Using Lami's theorem, what do we need? We need T1. So let's begin with T1. So T1 over the sine of the angle between the other two forces of T1, which is W and T2. That will give us 30 degree. Then we go for the W, since we know its value as the force, which is 500 divided by the sine of the angle between the other two forces will be T1, T2, and that will be 165. All right, so what do? We cross multiply, right? So T1 will be equals to 500 multiplying the sine of 30 degree divided by the sine of 165 degree. We can put all this in our calculator and just find the actual value that we got. Okay, if you put that together, you should be having, so now leave the answer in the whole number. Okay, let's see. We have 965.9. Let's approximate that to 966 Newton. So the first force, which is the tension in the first rope, is going to be 966 Newton. That is to the nearest whole number. We need to calculate for that of tension 2 as well. So from here we can say similarly, or and also picking T2 divided by the sine of the angle between W and T1. This is T2, so here 165 degree equals to, let's begin W, which is 500 divided by the sine of the angle between T1 and T2. T1, T2, which is also 165. Okay, let's cross multiply. Your T1, T2 will be equals to 500 times the sine of what? 165 degree divided by, this is multiplying this is coming as what? Sine 165 degree. And if you put in a calculator, since sine 165 is multiplying this, and in the same year, it will cancel to give you 500 what? Newton. So therefore, so by conclusion, we can say that the tension in the ropes are 966 Newton and 500 Newton respectively for the first rope and for the second rope. All right, you can check that the previous episodes that we did, all the ropes are attached or suspended above. So here the rope is one above, one word below. We can still use the concept we derived from the first episode on three group planar forces in equilibrium to resolve this. If you find this educative, don't forget to subscribe to the channel, leave a comment. Even thank you will be enough, or a thumbs up will be enough. Like the video by just clicking on the thumbs up button, and that is all. Thanks for watching.